MagicDec, a novel approach, challenges the conventional wisdom that speculative decoding, SD, is inefficient for high-throughput inference. By leveraging an intelligent drafting strategy and addressing the KV bottleneck with draft models and sparse KV cache, MagicDec achieves up to 2x speedup for Llama 27B32K and 1.84x speedup for Llama 3.18B on 8 NVIDIA A100 GPUs. This breakthrough is significant as it enhances throughput and reduces latency without compromising accuracy, particularly for moderate to long sequences. The efficacy of SD is evident in Figure 1, which illustrates higher throughput for SD compared to autoregressive decoding across various latency budgets. This finding underscores the broad applicability of speculative decoding in long context serving. The MagicDec system's performance is attributed to its ability to identify and address the KV bottleneck that scales with both sequence length and batch size, making it an efficient solution for high throughput and low latency inference. In this study, the authors delve into the optimization of speculative decoding for large batch sizes in autoregressive models. They focus on the trade-off between throughput and latency, particularly with the use of draft models and speculative decoding techniques. The total time taken for speculative decoding, TSD total, is composed of two parts: the time spent on draft decoding, TD, and verification time, TV. The authors introduce a mathematical formulation for the per-token latency of speculative decoding, TSDAVG, which depends on three primary factors: the draft-to-target cost ratio, TD, TT, the verification-to-target decoding cost ratio, TV, gamma, TT, and the expected generation length, omega, gamma, alpha. The authors also explore how different factors affect the speedup in speculative decoding. They find that a lightweight draft model is preferred for shorter model loading times and fewer computations, leading to a lower draft-to-target cost ratio, TD, TT. However, as sequence length increases, the bottleneck shifts to KV cache loading, which scales linearly with batch size, making it a significant bottleneck for large batches. The use of draft models with sparse KV is beneficial for long sequences due to their higher dim-KV, dim-model ratio, as seen in Figures 3b and 3c. The authors present theoretical analysis and expected speedup for Llama 27B32K and Llama 3.18B models deployed on 8x A100s with a speculation length of gamma equals 3. The results are depicted in Figure 2, showing the theoretical TD, TT versus batch sizes, TV, gamma, TT versus batch sizes, and theoretical expected speedup with self-speculation for a budget of 512 across different batch sizes. These figures demonstrate the potential speedup that can be achieved through speculative decoding, especially for large batch sizes and long sequences. The authors' findings suggest that the use of speculative decoding can significantly improve the throughput of autoregressive models, particularly when dealing with large batches and long sequences. This improvement is attributed to the reduction in per-token latency achieved by leveraging draft models and speculative decoding techniques. The study contributes to the ongoing efforts to optimize the efficiency of these models in real-world applications. In the context of speculative decoding for large language models, this paper explores the impact of increasing batch size on performance. It identifies a critical sequence length, synflection, where the bottleneck shifts from compute to KV memory, affecting the efficiency of speculative decoding. For sequences shorter than synflection, the speedup with speculative decoding decreases with batch size, while for longer sequences, the speedup increases. The analysis highlights that the draft-to-target cost ratio decreases with larger batch sizes due to the target model becoming more KV memory bound. This results in a theoretical speedup that improves with increasing batch size for longer sequence lengths. Factors affecting synflection include both the model and hardware, with a higher FLOPSTO memory ratio leading to a lower synflection. Additionally, the model itself influences synflection, such as Llama 3.18b having a higher synflection due to its grouped query attention mechanism. The paper also discusses the verification-to-target decoding cost ratio, which is desired to be close to 1. For sufficiently long sequences, this ratio remains consistently close to 1, indicating that the bottleneck changes from compute to memory. This shift in bottleneck forces the target model to be memory-bound even at large batch sizes, leading to an increase in speedup with batch size for S greater than synflection. The theoretical analysis is supported by figures illustrating the time breakdown of Llama 27B versus batch size, the draft-to-target memory ratio, and the theoretical speedup for different sequence lengths. These figures demonstrate how speculative decoding performance changes with varying batch sizes and sequence lengths. The paper concludes that understanding the interplay between batch size, sequence length, and model architecture is crucial for optimizing speculative decoding strategies in large language models. The paper discusses the design of draft models and their application in speculative decoding for accelerating sequence-to-sequence tasks. It highlights the importance of accurate draft models with constant KV cache, particularly with the streaming LLM architecture. This approach enables stable training-free methods for handling infinitely long contexts. The paper also presents experiments demonstrating the speedup achieved by speculative decoding, particularly with large sequence lengths and batch sizes. The results show that speculative decoding outperforms autoregressive decoding, achieving higher throughput and lower latency. The implementation details include modifications to the grouped query attention (GQA) to address optimization issues and the use of PyTorch CUDA graphs for reducing CPU overhead. The paper concludes by summarizing the speedup results across various batch sizes and sequence lengths, highlighting the effectiveness of speculative decoding for sequence-to-sequence tasks. The research paper discusses the trade-off between throughput and latency in long-context scenarios, focusing on speculative decoding for enhancing throughput and reducing latency while maintaining accuracy. It presents theoretical and empirical analysis, showing that as sequence length and batch size increase, bottlenecks shift from compute-bound to memory-bound, making speculative decoding effective for longer sequences, even with large batch sizes. The results demonstrate up to 2x speedup for Llama 27B32K and 1.84x for Llama 3.18B on 8 A100 GPUs. The paper highlights the need to integrate speculative decoding into throughput optimization systems as long-context workloads become more common. This research paper explores the optimization techniques for large language models, LLMs, to enhance their efficiency and performance in real-world applications. The authors delve into various strategies such as speculative decoding, batching, and quantization to accelerate LLM serving. They also discuss different models like Gemini 1.5, which is a next-generation model designed for efficiency, and LLMs that can handle 32K context, demonstrating significant advancements in the field. The paper begins by discussing speculative decoding, an approach that leverages speculative execution to accelerate sequence-to-sequence generation tasks. This technique has been shown to be effective in reducing the latency and improving the throughput of LLMs. For instance, En-Hsu et al. 31 proposed speculative decoding as a means to exploit speculative execution for accelerating seek-to-seek generation. Similarly, En-Hsu et al. 27 introduced attention sinks, a method that facilitates efficient streaming language models with attention sinks, further optimizing the efficiency of LLMs. In addition to speculative decoding, the authors explore the role of batching in optimizing LLMs. Batching involves grouping multiple requests together to reduce the number of calls made to the model, thereby improving the overall efficiency. For example, Together AI 29 discussed the importance of preparing for the era of 32K context, highlighting the need for efficient serving systems capable of handling large contextual windows. Quantization is another key optimization technique discussed in the paper. Quantization reduces the precision of the model's weights and activations, resulting in faster inference times and lower memory usage. En-Hsu et al. 32 proposed smooth quant, a post-training quantization method for LLMs that achieves accurate and efficient inference. Furthermore, En-Hsu et al. 33 introduced efficient streaming language models with attention sinks, which not only optimize the efficiency of LLMs but also enable real-time processing. The paper also touches upon the structural pruning of LLMs as a means to reduce their size and improve their efficiency. Mingjia Sun et al. 28 presented LLM Pruner, a simple and effective pruning approach for LLMs, demonstrating that structural pruning can significantly reduce the model size without compromising its performance. Finally, the authors discuss the importance of distributed serving systems for transformer-based generative models. Zhang En-Hsu et al. 34 proposed ORCA, a distributed serving system designed for transformer-based models, highlighting the need for efficient systems to handle the computational demands of LLMs. Overall, this research paper provides a comprehensive overview of various optimization techniques for enhancing the efficiency and performance of large language models. By leveraging speculative decoding, batching, quantization, and structural pruning, these models can be made more efficient and scalable for real-world applications. Here is a combined summary of pages 13 and 14. The appendix presents additional results, showcasing the efficacy of the proposed approach. Figure 6 illustrates the end-to-end speedups for Llama 27B32K with Tiny L Llama 1.1B and self-speculation draft, leveraging streaming LLM with a budget of 1024. The plot demonstrates the impact of varying batch sizes on speedup, with optimal gamma values annotated. Notably, the pre-filled models exhibit improved speedups, particularly with larger batch sizes. The self-speculation draft, a novel component of the proposed approach, facilitates efficient processing of input sequences. This is achieved through the streaming mechanism, which enables the model to generate output tokens concurrently with input processing. The mathematical formulation of the self-speculation draft is presented as equation 13, where the probability of generating token y_t given input x and previous tokens y_t is conditioned on the speculative token y_t. The equation is derived from the original sequence-to-sequence model, with the key innovation being the introduction of the speculative token y_t, which enables the model to anticipate future tokens and generate output more efficiently. The subsequent equations, 14 and 15, detail the computation of the speculative token probability and the update rule for the streaming model, respectively. These equations collectively form the backbone of the proposed approach, enabling the model to process input sequences in a streaming fashion while maintaining accuracy. Furthermore, the experimental results presented earlier in the paper demonstrate the efficacy of this approach, with significant speedups achieved for various model architectures and input sequences.